Pretty straightforward lesson today. So yesterday was quite brain heavy in that we had a look at rather complex proof, and it really was to give you an idea about how structured, logical reasoning and a thorough approach can prove something which is pretty obvious. But nevertheless, it showed the process. But as I said to you in last lesson, what we are required to do, RCD, is much simpler in that table itself. So these are notes you can take down. I will put them up in Google Classroom if you can't keep up. But the best way to do things is to write down. So in maths, when we say show or prove, it's a very, very precise process. And you'll find in mathematics, the reason why since you've been, well, probably ever since you've encountered a maths teacher, they've gone on and on and on about show you working out. You need to do this, you need to do that. Is because they know that maths is a precision sport. Okay? That when you take shortcuts with your writing down of things, when you're loose with the way you write or talk about things, it encourages a sloppiness of thinking which can result in poor maths. And that's not to say that mathematics is not a creative outlet as well. We talked about this at the start of the year, but you do need to have a creative mind to be a mathematician. You need to be able to imagine things in more than 3 dimensions, which is, as far as a sculptor goes, it's not that you have to get imagination deficient, but in order to produce stuff from your imagination, it requires precision, reasoning, logic to get there. And proofs is an example of that. And it's going to feel like I'm asking you to do stuff that is pretty simple, but the focus is on the precision of thinking rather than can you calculate stuff. Sadly, we only get to look at algebraic reasoning. One of my favourite ways of proving things is by induction, but we don't have time for that. If we end up with a bit of spare time, I might even show it to you as well, because the precision of thinking aspect of it is still very, very worthwhile for any mathematician. I won't go through it unless I have to, kind of thing, because of time, unless I can, I mean. But yeah, as it says there, we use these proofs to show that multiple theorems are true. Do you remember what I called something which is so fundamental it doesn't need to be proven? What was that called? Sorry? No? I have used trivial before. Yeah, axiom. Yeah. I have used trivial before, which is sometimes they will say that as well. The proof of this is trivial, which means it's kind of self-evident. Like if I prove that 2 odd numbers are equal to an even number, once you've done that, proving 2 even numbers add up to an even number is trivial. 2i plus 2j equals 2 times I plus j, which is equal to 2k. It's pretty trivial once you've done the hard work of an odd plus an odd equals an even. Okay, so anyway, so axioms are things like 1 plus 1 equals 2. And if I remember, I'll try and find a video which explains why 1 plus 1 equals 2 in about an hour and a half or something. So induction, deduction, geometric proofs. Proof by contradiction is a good one, where suppose it's not true, and then you show that if you suppose it's not true, it doesn't work, and therefore it must be true. That's proof by contradiction. My nearly 17-year-old daughter tries to prove things by contradiction all the time. No, she's just contradictory all the time. algebraic reasoning is a fairly simple approach, right? So this is what we looked at. This example is what we looked at on the other side. Last lesson. So I'll do it really quickly. I know I did it last lesson, so it's really just to be part of your formal notes to start with. So, and through it, this is why I'm recording it as well, because I don't think it'll capture very well in notes unless I do copious notes. Properties of a proof that we always use one side only. In this case, I'll use the left-hand side, so it's the more complex of the two sides. It's usually easier to simplify one side rather than to make the other side more complicated. So we start off with one side, and typically we go LHS for left-hand side, and then we write down that left-hand side. I write it on the right-hand side just to be confusing. And then we manipulate until we get to the right-hand side. So in this case, I'm using equivalent fractions. Oops. I'm using equivalent fractions in order to get what I'm looking for. Common denominator. And then there are two ways of finishing off that they want that the Maths AA, the IB want you to be aware of. One way is to write this. It's an equal sign with an extra bar, and it's like a strong equal sign, I suppose. And it's called the identity operation, and it means that this is the rule. Rather than just saying, hey, left-hand side is the same as the right-hand side, do what equals mean. It's saying, this is the rule. This is what has been shown. Right? It's an identity. It's like an axiom, but it has been proven. You can always use this. It is a rule. Left-hand side is equivalent to the right-hand side. Through my voice, I'm trying to give a strength to it, I suppose. So that's what it means. So you say left-hand side is equivalent to right-hand side. It might be that you just write equals right-hand side here, and then write QED. Quo demonstratum, as it is shown. Okay, I personally go equals right-hand side QED. I don't write LHS equivalent sign RHS. But you might see it in a test or something or an exam, so I thought I'd just let you know. But there's lots of ways. Like I remember when I was at university doing this maths, the lecturer always just used to use a hashtag at the end. Well, they weren't called hashtags then, but it wasn't like in the 1860s. But that was just a way of saying, so that was effectively ta-da kind of thing. They all mean that. They all mean ta-da. Okay, any questions? I'm about to move on to the next page, and I appreciate for some of you might not have had a chance to write everything down. The notes will be on Google Classroom before the end of the lesson, so just be mindful of that. The next couple of pages are just what we went through last time, and I've added the side note here. The following two pages are beyond the scope of the course. Don't stress about it. All of this is really going from, let's say we've got a very vague concept, like show that the sum of two odd numbers. How do I go about formalising it and then proving it? So it's quite, a little QED lift there for some reason. It's quite formal in its approach. Here's an example though I thought we might just go through and sort of say, you've seen this example before. Not example, I hope. You've seen this rule before. A squared minus b squared equals a plus b times a minus b. This is called what?
Double distribution.
It's not called double distribution. It's not called, how about I tell you? Yeah, dots. It's difference of two squares. It basically says that if I have the square of one number and I subtract the square of the same number, unless you might call it something different, I don't know. But, so I've got a difference, subtraction of two squares. difference of two squares, then it's equal to a plus b times a minus b. So we can sort of say 144 minus 25 is the same as 12 minus 5 times 12 plus 5. So it's equal to 7 times 17. There you go. 144 take away 25 is the same as 7 times 17. That's what it means, but we need to prove that it's true. Now, when you look at this, you might be tempted to go for the left-hand side because it's on the left, but in this instance, it's actually simpler to work from the right-hand side. So the proof is very specific. Remember, we only focus on one side, so the proof is right-hand side is equal to a plus b times a minus b. Use whatever your favourite method is. Have we talked about chicken baking in this class?
No.
Don't say like that.
Yeah, I think well, not chicken baking as such.
So it looks like a chicken beak. Blue's the top beak and red's the bottom beak. And it basically means multiply each thing by in the one set of brackets with each thing in the other set of brackets. So we end up with a times a is a squared, a times minus b is minus ab, b times a is positive ab, and b times minus b is minus b squared. The two terms in the middle cancel out, so we're left with a squared minus b squared, which is equal to the left-hand side, q, e, d. So note that I only worked on one side. You don't work on both sides because errors can creep in. Just as a bit of fun, you might have seen this before. So don't write this next bit down. Sure, Siri. Don't write this bit down. It's just a bit of fun to see how you can cope with this. It doesn't follow the usual proof kind of things, but I'm going to prove. Which one shall I do? I'll do this one. This is a proof that 0 equals 2. Okay? Which is going to be really good.
What?
Because it means that all of you are going to give me $2 and I'll give you nothing in return and it'll be even, so that's good. So here we go. Let's see if I can remember how to do this. X equals 1. Or let x equal 1. Then x squared is equal to 1. Because the square of 1 is 1. X squared minus 1 therefore equals 0. Yeah? Okay, cool. Using dots like I did above there, that's x squared minus 1 squared. So that's x minus 1 times x plus 1 is equal to 0. Then I'm going to divide both sides by x minus 1. And I've got x plus 1 is equal to 0. And since, oops. Try that again. Since x equals 1, 1 plus 1 equals 0, and 2 equals 0. Pay up now? No? Alright. So that proves that 2 is equal to 0. Have a chat with the person next to you, or turn around. We know 2 does not equal 0, so what did I do wrong? I'll pause the video so that we're not recording silence. So we've had a bit of, for the video, we've had a bit of a discussion. Roger and Will, there may have been others as well, but Roger and Will observed that at this point, when I divided out the x minus 1, I had an error because I was dividing out by effectively 0 here, 1 minus 1. Yeah. Anyone else get that? It's not here? Yeah, well done if you got that before it was explained. That's good. So the reason why I did this is not just for a bit of fun, because there's heaps of proofs like that where there's a logical error somewhere, but it's not immediately obvious. The reason why I did that is because it demonstrates why it's really important in a proof that you stick with one side only. Because I could not have done that. I could not have done that if I was sticking with one side of an equation. If I had tried that with one side, there would be no other side of the equation to divide these out by. So, proving things like this opens you up to errors of calculation that are really easy to make, like that. Really easy to make. So, by sticking to one side and manipulating it to get to the other side, we eliminate any flaws in logical thinking as a result. And that's why we do it, if that makes sense. Okay. So, in your textbooks, can you please turn to, very early in the textbook, I just missed a page, so can you please turn to page 55? This does not make for good video watching, but I'll only be a sec. Actually, no, I'll just stop the video now, but on the theory notes, I'll write the page reference and stuff.